Yes. So, a while back, I did some research on Parkinson's, just on my own because I was bored, and a lot of the videos online and references and Earl's content even doesn't really clearly demonstrate what's going on with basal gangliar control. So, real quick, we'll just give a basic overview of how the basal ganglia can help to plan motor functions. So basically what happens, the stuff that we know so far, a pyramidal cell in the cerebral cortex sends a projection to the putamen, and then the putamen has a synapse with a projection that is sent to the globus pallidus. The globus pallidus synapses with a projection in the thalamus, and then that projection travels, I believe, in the internal capsule back to the same region of the cerebral cortex to cause voluntary skeletal motion. So that's how you plan a movement. But he hasn't really demonstrated this along with the Substantia nigra, which literally means black substance, and the subthalamic nucleus. So I'm going to try to do that for you guys right now. We've drawn the Substantia nigra a lot closer to the basal ganglia than it would be. It would actually be down around here in the midbrain. The subthalamic nucleus is around the same region. So what's really happening relies on two different pathways. One is a direct pathway that actually helps to initiate movement, and that's the one we're going to talk about right now. So this kind of relates to Parkinson's. We'll touch on that a little bit too in the next video. So the projection right here from the cerebral cortex to the putamen. Actually, before we get into that, let's talk about what each one of these structures does so we can actually relate this. The thalamus, the best example I've ever heard of somebody explaining it is that it's like a dog. It always wants to run, and basically the running in this case would be voluntary skeletal motion. So the thalamus just always wants to send these projections to the cerebral cortex to cause movement. That is its job. And when it is uninhibited, that is what it does. There's no off switch, except for the one we're going to talk about next, which is from the globus pallidus. So this globus pallidus is really kind of like a leash for the dog. This is a really good leash, I know. And it stops the thalamus from sending all of these excitatory neurons to the cerebral cortex to cause motion. So the globus pallidus is actually going to send a neuron right here to the thalamus that inhibits the thalamus, and that's just under normal circumstances. So we will draw the excitatory neurons in green and the inhibitory neurons in red. So we're going to kind of work backwards here. To keep going though, the globus pallidus, we know that its function with this inhibitory neuron is to stop the thalamus from working. So if that was the only structure associated in the basal ganglia, we would never be able to move. The putamen helps us out with that though. It basically cuts the leash to the thalamus and lets it run. So the putamen also sends an inhibitory neuron to the globus pallidus. So we know the globus pallidus's job is to stop motion from the thalamus, but the putamen's job is to stop the globus pallidus from stopping the motion. So these two inhibitory neurons can kind of be seen as canceling out. So when we use our basal ganglia, the putamen cancels out the effect of the globus pallidus, which allows the thalamus to initiate motion. So just to clear that up, the green we're going to use for the excitatory neurons. So the cerebral cortex, when we want motion, is exciting the putamen. The putamen works basically to inhibit the globus pallidus, which normally inhibits the thalamus. And the thalamus, once uninhibited, can then send these excitatory neurons back to the cerebral cortex. So that's our general basal gangliar functioning. We'll talk about the Substantia nigra now and the subthalamic nucleus. So this alone wouldn't be as effective without the help of the Substantia nigra. And again, this is the direct pathway that is causing movement, because the Substantia nigra has jobs in both the direct and the indirect pathway that we'll talk about later. So the Substantia nigra basically has these dopaminergic neurons, which are neurons that use dopamine in a synapse to affect synaptic transmission, which we've been talking about. So these dopaminergic neurons come from the Substantia nigra, and they actually bind to dopamine receptors on the putamen, on the inhibitory neuron coming from the putamen. So this dopamine neuron basically is sent up to the putamen, and it binds to a dopamine receptor on the inhibitory neuron traveling to the globus pallidus. Now these dopamine neurons, we'll color these in blue. What dopamine does to this inhibitory neuron is it basically makes it stronger. It bolsters it. So dopamine is bound now to this neuron, making it stronger, which better inhibits the globus pallidus. So now the putamen and the Substantia nigra basically are working to shut off the globus pallidus. And we know that the globus pallidus has been shutting off the thalamus. So if the putamen and the Substantia nigra are doing their job correctly, sending dopamine to this inhibitory neuron, we will see movement. The thalamus is then free to send those synapses to the cerebral cortex, which is the basis of how we actually move, and that's motor planning. Not to be confused with feedback and feed forward from the cerebellar, which helps with real-time motor adjustments and muscle memory. So the subthalamic nucleus over here, this little guy, has a pretty simple job. It sends an excitatory neuron from the subthalamic nucleus to the dopaminergic neuron of the Substantia nigra. So basically, the Substantia nigra can't work without the subthalamic nucleus activating it. So following with our theme here, the subthalamic nucleus is sending an excitatory neuron to the Substantia nigra, so we'll color that in green as well. So that's the basic idea right there. And you can see clearly now the effects of shutting off this excitatory neuron. And in Parkinson's, we see basically two things. The excitatory neuron, or I'm sorry, not the excitatory, the dopamine neuron from the Substantia nigra going to the putamen in Parkinson's disease will often degrade and wear out and become useless. So with Parkinson's patients, sometimes we will see that pathway be eliminated, which doesn't help the putamen anymore and shutting off the globus pallidus as well. So if you have no dopaminergic neuron going from the Substantia nigra to the putamen, the globus pallidus isn't really shut off that well, which means that you're not going to be able to produce that voluntary skeletal motion like we see in some Parkinson's patients. So basically, that's the basis of why it's so hard for Parkinson's patients to do something like sit up out of a chair. They're not able to inhibit the globus pallidus very well, and so it takes them a long time to do these compound skeletal motions that come from the thalamus.